Hi, this is Mr. Barron. I'm going to be teaching you about the common ion effect. I'm going to be using the practice exercise located within the sample exercise 17.1 on page 723 as my example. So if you want to follow along with where I'm getting the question, you might want to turn to page 723 of our book. Now, let's talk about a acid, HNO2. It's a weak acid. This acid, which is called nitrous acid, does indeed break down a little bit into hydrogen ions and its conjugate base. So don't forget, this is the conjugate base of this weak acid. If it was a strong acid, all of it would ionize, all of it would break apart in a solution. So this one doesn't fully break apart. Now say to this, I don't know, this reaction here, we add a salt. And the salt we add is potassium nitrite, KNO2. All right, now potassium nitrite is completely aqueous in our solution. And I'm going to draw this sort of in a side box here. Since it's totally aqueous in our solution, it means it fully breaks apart into potassium and nitrite ions because of its aqueous nature. All alkali metal salts are basically aqueous. So potassium and all the other alkali metals, we have to remember that they're always spectators because anything that they connect to, they make aqueous, so they never really connect and precipitate out. And because of that, we actually ignore. So when we say we add potassium nitrite to our solution, we're actually saying that we're really adding NO2 minus to our solution. So let's talk about what we're doing. So we had this weak acid in solution, and then we added a bunch of potassium nitrite, and it upped the concentration of nitrite in this equilibrium. Because it has upped the equilibrium of this, what it does is what little hydrogen ions have fallen off of this nitrous acid, it drops the concentration of the hydrogen ions as it shifts the equilibrium to this side and thus increases the concentration of nitrous acid. So what we end up having is we end up having a lot of HNO2, pretty much no hydrogen ions, and a lot of NO2 minus. And this is the common ion effect. It basically is when you have a weak electrolyte and the ionization of it, this is my weak electrolyte, how much H plus falls off of it is decreased by adding ions of its conjugate base, meaning adding NO2 minus, which is the conjugate base to HNO2, and I got that from the KNO2. That's causing this to go down. This ionizes less because it's already a weak acid. Only about like maybe 2% of it ionizes to produce hydrogen ions. And that's decreased even further because of this equilibrium shift caused by the addition of the conjugate base ion, which came from the potassium nitrite. All right, now what we're going to do is we're going to talk about how to figure out the pH of the solution when we do such a thing. So now I'm going to be doing the practice exercise that's located in 17.1 on page 723. What we have here, and I have to write out the equation, is we have HNO2 in equilibrium with hydrogen ions and nitrite ions, NO2 minus. And then it tells us that we begin with 0.085 molarity of nitrous acid, 0.085 molarity. Oh my goodness, this sounds like an ice table because I have an initial amount. And what I'm going to have to figure out the pH, because pH I'm going to write down way down here. Remember, pH is the negative log of hydrogen ions. The only way I can figure that out is to figure out my hydrogen ions in equilibrium. So it is indeed an ice table. So it's 0.085 molarity for the nitrous acid, and then we have nitrite ions, which we know the starting concentration of this because it says we start with 0.10 molarity of KNO2, and that basically dissociates and creates more of the nitrite ions. All right, now hydrogen ions 0 because it hasn't broken apart yet. So now what we have to do is figure out the change. So what's going to happen is that this is going to decrease as it ionizes. So some value minus x. Since it's 1 to 1 to 1, all my values are nice and simple. They're just x's. And this is going to go up. And this is going to go up as well as it ionizes. All right, so let me write it out. 0.085 molarity minus x. Keep that together. And then, of course, I have x, and then I have 0.10 molarity plus x. Now, I'm going to be bad and not write my units for a little bit, and I'm going to write out the equilibrium expression. So Ka, of course, is my products over my reactants. So it's going to be x times 0.10 plus x. I know I didn't write the molarity there, but I'm doing this just to keep my math simple. And then over the reactant, which is 0.085 minus x. All right, there's something interesting I need to consider here. I know my Ka in this particular problem, and I'm going to rewrite this whole thing down here. My Ka, it tells me in the beginning my equilibrium constant is 4.5 times 10 to the negative fourth, and that's equal to this whole thing, which is x, 0.10 plus x, 0.085 minus x. Okay, now we have to solve for x to figure out the hydrogen ion concentration, which will tell us our pH. Now, let's think about how we can avoid a quadratic and make our life a little bit easier. See what I have in parentheses? See how it's some number plus x and some number minus x? Well, these x values, not this one, but these ones right here, that x is going to be really small. We know it's going to be next to nothing because, I mean, the nitrous acid is a weak acid. There's such a low amount. We can assume these two are 0. So when I do my math on this problem, it's going to be 4.5 times 10 to the negative fourth equals 0.10 x over 0.085. Now I have to solve for x, so I'm going to type this into my calculator. So it's 4.5 times 10 to the negative fourth divided by, or no, sorry, multiplied by 0.085 and then divided by 0.1. And then I find out that my x, which is also my hydrogen ion concentration, is 3.825 times 10 to the negative fourth. And that's in molarity. So if I want to figure out my pH, I'm going to have to take this number of x, which is this x right up here, and plug it in right there. So I have to take the negative log of this value that I've solved for x, and let's see what I get here. I get a pH of 3.417, which rounded is the correct answer of 3.42. There we go.